Hello, my name is Robert Strandh, and this is part 3 of my series of presentations entitled Creating a Common Lisp Implementation. Just as a reminder, the topics that are covered in this presentation series are choices of implementation language, and in practice we have only two choices, which is Common Lisp and something else. And I'm going to use the language C as the example of something else, but it makes no big difference which one the other one is. Another topic covered is implementation strategies for the evaluator, and division of code written in Common Lisp and code written in the implementation language. That is, we're trying to write as much as possible in Common Lisp. So the topics that are not covered in this series would be how a Common Lisp compiler works, and if there's demand, maybe I can prepare a different series about that topic. I'm not going to talk about how different strategies for memory management. And I did present an abstract machine, but I didn't present any details of how that machine works. And I'm not planning to. And also, I'm not going to talk about how real hardware processors work. However, there has been some interest for these topics. So if there is demand, I might create some of them in the future. So remember the general assumptions that I discussed in part 1. We want to use Common Lisp as much as possible for the implementation of our Common Lisp system. We said that the resulting system should not be too slow, but we're not interested in extreme speed at this point. The implementation we're creating is a pre-ANSI implementation, so it has no classes and no generic functions. And we will see, we will revisit that decision at some later point. So we started with strategy 1, which is to write a small core in, say, C. We wanted that subset to be very small. And then the plan was to add more functionality, and that functionality should be written as much as possible in Common Lisp. But with this strategy, we ran into a number of complications. We ended up with a lot of C code despite our best intentions. We ended up having to write reader in C and evaluator in C and some other things. We may end up with multiple versions of the same module, perhaps a simplified C version and a complete Common Lisp version. Say we might write a very simple reader in C that can read only the rest of the source code in our system, and then have a complete Common Lisp reader written in Common Lisp. So we have more code than we would want to maintain. Another problem was that a lot of the Common Lisp code that we wrote was not written in the most natural way, and the reason for that was the order between the modules that had to be loaded on top of the core. So for each module we loaded, only the subset defined by the modules already loaded could be used, and that made the code look not particularly natural. There are many often implicit dependencies between modules. When I say implicit, is that they're hard to document. So the resulting system is hard to maintain because it's tempting when a module is modified to use some feature that's not available at that point in the creation process. And also recall from part 2 that we ended up with this kind of, I think it was part 2, that we ended up with this kind of compile time dependency diagram where red arrows mean compile time dependencies. So in particular, we have a lot of dependencies between macros. For instance, DEFMACRO must exist in order for the macro setf to be defined and so forth. And what we're trying to do today is to break some of these compile time dependencies, which were the cause of some of the unnatural looking Common Lisp code. The other thing we discussed last time was the abstract machine. I'm not going to repeat that again. I'm just reminding you that we assume that we have a core written in C, and that core contains a bytecode interpreter, and that bytecode interpreter operates on an abstract machine that looks kind of like this. Now, this abstract machine is not terribly different from a real machine. So in fact, if it's a native code or bytecode, doesn't really matter here. So the question for this presentation, number 3, is what can be done to break all these dependencies that we ended up with and that made the code unnatural if it's Common Lisp code, or we ended up writing too much C code. So let's imagine a hypothetical situation. We have managed to write a conforming Common Lisp implementation somehow, but we wrote the evaluator in C, perhaps as a direct interpreter. So we have a conforming Common Lisp implementation. The result is slow, so now we want to write the bytecode compiler. Since we have a working Common Lisp implementation, we can write this bytecode compiler. We can write it in Common Lisp. And this bytecode compiler is the core of the strategy 2 that we're going to discuss today. So just a reminder of the compilation process of Common Lisp and also of more traditional languages. The Common Lisp compiler translates an input file to an output file. And in order to do that, it operates on these 3 environments. The startup environment is the runtime environment that is used to start the compiler from. And then when the file compiler starts up, 2 more environments are created. The evaluation environment, in which evaluations take place at compile time. So whenever the compiler sees eval when compile top level, that's the environment used for evaluation. And then there's the compilation environment. And just like the evaluation environment, it's created when the compilation starts. So it's initially empty. And it contains definitions and declarations maintained by the compiler. If you look in the hyperspec or in the standard, you will see many macros such as defun, defvar, defgeneric, etc. that mention what happens when the compiler sees that an invocation of that macro as a top-level form. And then there's information that is entered into the compilation environment. So if we look at this diagram here and we imagine what could possibly be part of the output file, where does the information contained in the output file come from? Well, it obviously comes from the input file. There's the source code in the input file will generate some information in the output file. It comes from the code generator of the compiler. So the compiler here will generate some instructions, perhaps for the abstract machine, and those instructions will be part of the output file. But crucially, the third source of information in the output file comes from the macros in the startup environment. So there could be names of functions, variables, names of packages, and so forth that the macro expander generated. So if you look here, there are some macros in the startup environment here that will be expanded by the compiler, and the result will be part of the output file. And what's important here is that the definition of these macros vary between different Common Lisp implementations. So they have to be the exact definitions for the specific Common Lisp implementation that we're writing. Now, if we compare that to the compiler for a traditional batch language, it looks like this. I already mentioned this in part 1. It only has a compilation environment which is initially empty. So there's absolutely no information coming from any existing runtime environment or whatsoever. Everything comes from the input file or files that it includes. And so the output file doesn't contain anything from the system itself. It all comes from the input file and the compiler. And that's the crucial difference between a Common Lisp compiler and a compiler for a traditional batch language. So if we compare those to a compiler for a batch language can run anywhere because the environment from which it started doesn't influence the output generated by the compiler. But because of the macros, a Common Lisp compiler must in principle be executed from the same Common Lisp system that it's written for. And I'm saying in principle because we're going to see how we can get around that. So aside from this pesky little problem that it has to be run from its own Common Lisp implementation, nothing prevents us from writing a Common Lisp compiler in portable Common Lisp. And it could be executed then in any conforming Common Lisp implementation. But there is this pesky little problem that we have to solve, namely that the macros cannot be the macros of any different Common Lisp implementation than the one that we're writing the compiler for. So what if we found a solution to this pesky little problem? Let's say we just imagine that there is a solution to it. That is, we could somehow get the macros for our own Common Lisp implementation, but on a different so-called host Common Lisp system. Well, then we could execute the compiler on that host Common Lisp system. So we could take our own input files and generate our own compiled files. And then we would have we could in fact even feed the compiler itself as input, and we would then have the compiler compiled to bytecodes. And if we just have a simple bytecode loader written in C in this core core of our target system, we could then load the compiled compiler. And we would no longer need the initial interpreter at all, because the interpreter is not needed in order to load bytecode files. And so this is the essence of cross-compilation. So in fact, if we can get away with this somehow, if we can solve this problem, then we can compile our system. We can generate our system by cross-compiling source code written in Common Lisp and then just loading it into our own system. So in order to see how we can solve that little problem, we need to first, there's going to be a lot of code from now on. So I'm going to take a little bit of time to explain how this code could be structured. So let's first explore how we would typically write our package structure of our final target system, the one that we're implementing. Well, a very nice way of structuring the packages is to have one single package called the Common Lisp packet. Well, it would have a nickname of CL, of course. It would use absolutely no other packages, and it would export all the standard symbols that are mentioned in the standard. But there would be no code written in that package. And then there'll be any number of implementation packages, perhaps one for each chapter in the standard. So, for instance, that could be one package called target-cons, target being the hypothetical name of our own implementation here. And that package would use the common-liap package. So if you write a function in the target-cons package, then if a standard symbol is mentioned, it will be the symbol from the common-liap package. But any other symbol, like loop counters or whatever, will be specific to the target-cons package. So typically, for instance, you would have a file in which you define the function mapcar. Then it would start with in package target cons, and then there would be define mapcar, etc. Now, the symbol mapcar in this example would come from the common-liap package, and so would the symbol list. But the symbol fun would not be in the common-liap package, it would be in the target cons package. So the idea is to have one single common-liap package with no code or no symbols in it other than the standard ones, and then to have a number of implementation packages that use the common-liap package. So for instance, we might have a file like this to compile. It would contain the definition of mapcar, which we saw already, I believe, in part 1. And it's a simplified definition of the mapcar function. Now for cross-compilation, we're going to modify this package structure just a little bit. It's not going to be too bad. We're going to define a package called target-common-lisp. And this will be a package defined in a host common-lisp system that would not have a package of this name, of course. And then we would modify all of our implementation packages to use, or we would have special cross-compilation versions of those package definitions. They would still have the same name, target cons in this case, but they would use the target common-lisp package instead of the common-lisp package. Otherwise, everything else would look the same. In particular, all the code in all the implementation packages would look identical, whether it's cross-compilation or native compilation. And now let's see what we can do to cross-compile on a host common-lisp system. So we might have a ASDF system definition sort of like this. I'm going to depend on this code utilities, but only for one particular function. I'll get back to that later. And so the components of this ASDF system, there would be the package definitions, of course, the target common-lisp package, the cons package, the evaluation and compilation package, the data and control flow package, and so forth and so forth. And then there will be a file that will load up the target macros, and that's the secret to our cross-compilation here. We will somehow manage to load our own definitions of our own macros into this host common-lisp system without interfering with the existing definitions of those macros in the host system. So I guess I already mentioned this, but here are some more packages like target data and control flow, target evaluation and compilation. These correspond exactly to the chapters of the standard. So the target common-lisp package would look something like this. we would have a def package form that defines the target common-lisp package. It won't use any other package. It will import a certain number of symbols from the host common-lisp package. And this is a readtime form, hash dot, and it will loop over all the symbols in the host common-lisp package. And it will look at whether the symbol is a lambda-list keyword or if it's a special operator. In that case, we push the symbol name on this result list, and that becomes the list of imported symbols. So we import into our target common-lisp system all the host symbols that represent special operators and all the host symbols that represent lambda-list keywords. And what do we export from the target common-lisp package? Well, basically all the symbols, the names of all the symbols in the host common-lisp package, all the external symbols. So we have now constructed a package that has a few symbols taken from elsewhere, namely the lambda-list keywords and the names of the special operators. All the other symbols are local to our target common-lisp package, and we just have stolen the names from the host common-lisp package. And so, as you can see here, we do loop over the external symbols of the common-lisp package, and we just push the symbol name onto the result here. So this will be all the standard common-lisp symbols are exported. Now, in order to load the target macros, recall that there was let me go back to that one. The last file here was a file to load the target macros. And that file looks like this. It is executed in the host common-liap-user package. And what does it do? We start by stealing the definition of the host macro called DEFMACRO. So the macro function in our own target common-lisp package with the name DEFMACRO will have a macro definition which is stolen from the host macro called DEFMACRO. And what else do we do? Well, again, we loop over the symbols of the host common-lisp package. And when we find a symbol that is f-bound, that is, it has a function associated with it, and it's not a macro, and it's not a special operator, we import it. That is, we set the f definition of that symbol in the target common-lisp package. We set it to the same f definition as the symbol in the host package. Basically, we borrow all of the standard functions from the host common-lisp. So we will have definitions of car and cooter and cons and member and all the other standard functions, but we will not steal the macros and not steal the special operators. And then we can start loading our macro definitions, and we're going to start by loading the macro called DEFMACRO, and then we're going to load the macro called lambda, and then we're going to load the macro called return, and then the when, and so forth. And we can, in fact, load all the macros in our own Common Lisp implementation. These are our definitions. So let's just see how that works out. So the first macro we want to, the first file we load is a file containing the definition of DEFMACRO. And this looks a little bit spooky here because we can say DEFMACRO DEFMACRO, name lambda-list body, and then we call a function parse-macro. Now, first of all, let's examine why this works here. Well, what's going to happen is we're in the package target evaluation and compilation. So DEFMACRO is going to be a symbol in the target-common-lisp package. But we've stolen the definition of DEFMACRO from the host. So we can actually use the macro DEFMACRO because it doesn't do anything particularly suspicious in the host. It just defines a macro. But the macro that it's going to define is, of course, the name of it is in our target-common-lisp package. And what does the DEFMACRO do? Well, it calls the parse-macro function. This, I happen to steal that from the cleavir-code-utilities, but it's a function that was defined in Common Lisp, the language, 2nd edition. And I can assure you that it can be written in portable Common Lisp. All it does is it takes a name and a lambda list and some code, and it produces a lambda expression. That lambda expression is basically, when compiled, is the macro function for the macro. So the result of this is a lambda expression, and so the expansion of the DEFMACRO will be a lambda expression, and when that is evaluated, it turns into a macro function. So now we have our own definition of the macro DEFMACRO, and there was nothing particular we had to do. We didn't have to define this in any other way. We didn't have to use setf macro function or anything like that. We just used the most natural way of defining it, which is to call DEFMACRO. So now we have our own version of DEFMACRO in the target-common-lisp package. And now we're fine because whenever we mention DEFMACRO in the future, we will have our own version of DEFMACRO. So, for instance, the macro definition of lambda, it will occur in the target evaluation and compilation package. And we will just say DEFMACRO lambda, and it will be a very natural definition of the macro lambda, because now we have our own definition of DEFMACRO available. Similarly, in the target data and control flow package, we can say DEFMACRO return, and it'll expand to return from nil, and so forth. So all of these macro definitions look natural, which they didn't do in our strategy 1. Here's the when macro. It's no problem either. So there are some minor issues with this idea. The compiled files will refer to the package called target-common-lisp rather than to the package common-lisp. And that's because all the symbols that we used were in the target-common-lisp package. So when these compiled files are loaded into our core system using the bytecode reader, it's going to look for a package called target-common-lisp rather than a package called common-lisp. To handle that issue, when the compiled file is loaded into the target system, we just rename the Common Lisp package so that target-common-lisp is a nickname of the Common Lisp package, and we've solved that problem. There's some other minor issues as well. There could be target-specific functions that are executed by target macro expanders. So for instance, it could be that when we expand complicated macros such as, let's say a def generic, we do that by calling some of our own helper functions. And of course, those helper functions must be loaded into the host system beforehand, before we can start expanding those macros as well. And there's some other issues that I've also omitted, which is that many macros have compile time side effects. For instance, the defun macro has a compile time side effect to register the name of the function so that it can be recognized as existing by the compiler in the future compilations. But these are simplifications. I can't go into the detail of how all of these issues are solved. So let's see what we have accomplished here. Well, now we can compile any target code on the host just by loading our own version of our own macros and the helper functions for those macros. And when we say any code, that includes the evaluator and the reader. So nothing prevents us from taking the source code of our evaluator and of our reader written in Common Lisp, compiling it this way in order to obtain compiled target files, and then load those target files into our own core system. And that means that the C code for those modules that we had to write with Strategy 1 are no longer necessary. And the only C code we're left with is the bytecode interpreter and the abstract machine. And in fact, we can do even better. We don't have to compile to bytecodes. We can compile to native code. We can just define a facile format that contains native instructions instead. It remains a simple file translation compiler. It's no difference at all. It could be a little bit tricky to build a target system from compiled files, because if we don't have a bytecode loader and we don't have any native code loader either, it could be a little bit tricky to get that to work. But in fact, it works, because that's essentially what SBCL does for its bootstrapping procedure. This is documented in a paper by Christoph Rhodes, and the title of the paper is SBCL, a sanely bootstrappable Common Lisp. And so that concludes the presentation for part 3. And for part 4, recall that what we've done so far is we have been creating a pre-ANSI Common Lisp implementation. So it has no classes and no generic functions. So in part 4, what we're going to do is we're going to examine the impact on our implementation of not having CLUS from the start. And I hope to see you for the part 4, which of course hasn't been scheduled yet, and we don't know when it will take place. So see you around.